Okay, good evening to everyone who's present today. It's just one student right now, Dharani. So, good evening. So, we'll start with our week 10 doubt clearing or problem solving session for the course uh, Smart Grids Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena. I am Swastik Sharma. I'm a PhD candidate at IIT Kanpur and I am a PMRF scholar as well. So, it's yeah, physical type. Yes. Hmm. So, last class we were discussing about, we started with demonstrations. So, the course has culminated to a point where we learned all about the control strategies, energy management schemes, etc., etc. And now and now the instructor started presenting you some case studies or some demonstrations of the smart grid concepts on real-time simulation platforms. I discussed in depth last class what are real-time simulations and how are they conducted using RTDS or local RT or typhoon. So yeah, so this in this class, the instructor started with what is real-time simulation, which I've already discussed. That when you're presenting some control strategy, you should know if in real time it's able to it's able to match the conditions which are there in real time, right? So let's say in your MATLAB program, your solution converged in 5 milliseconds, but can it converge in 5 milliseconds in real time as well? So that is something that you test using RTDS. And in RTDS, not just RTDS, real time simulation, there are four testing uh, four validation steps, where the first step is software in loop validation. So I've taken this again, I'm giving this disclaimer, I've taken this PPT from my senior. She graduated last year. Her name is Dr. Shreyasi Stone. So I've taken this slide deck from her. And so the first step that you do is you prepare your software in a real-time simulation platform, which is RSCAD for RTDS. And there you test your control logic or your protection logic and see if it makes sense in real time. Then you move your control logic or protection logic out of that software platform in a hardware setup, and there you do controller hardware in loop validation. After that, once it start making sense, so what you do, you remove the power hardware as well from your simulation platform, and then you do power hardware in loop validation. Once everything is ready, if everything is able to you're able to perfectly validate everything, then you move on to field validation, because anyways, so you validate something, but at the end goal is it to be able to be deployed in field, right? So that's something that you have to follow these four-step procedure. Now, the RSCAD is much more relevant for your transient study. So there exists transients in the system, right? So in real time, how these transients have an effect over your control strategy is something that you should be able to know. So that is something that you could do in real time simulations. So let's start. So this week we started with first the demonstration on demonstration. It's a bit wide. Yeah, Dharini, did you check my last week's? So you had this question, right? Why ID is there? So were you able to? So did you check? Did you get the concept right? Okay, great. So let's start with the demonstration. So in this demonstration, the instructor took an AC microgrid in which we had a storage system, which was lithium ion battery, a diesel generator, a load, and a PV supply. And it was connected to a three-phase grid which had a 480 volt which had a 480 volt specification, and all was connected to a circuit breaker at the point of common coupling. Now, I said 2 pages. Yes. Hmm. So you studied the operation of AC microgrid, right? Now you want to optimize the performance of your control strategies. How will you do it? You will do it through continuous real-time simulation. And now, for this, the circuit that you've chosen is a circuit which has storage as well as a diesel generator. We already know. Can someone tell me why when the someone get Dharini is already only there. Yeah, Dharini, can you tell me? Let's say my circuit breaker trips and the microgrid is in working in isolated mode. Who will who will provide voltage and frequency control out of the three generations present? So what you want is you want control over the voltage and frequency. Who do you think would be better suited for that? Could it be wind? Sorry, could it be PV or diesel generator or your lithium-ion battery? Okay, no, not battery. Um, what if it discharges? So you want control over AC. So your generator, diesel generator, which is a synchronous machine, you generally use a synchronous generator, is better suited for that purpose because it is able to provide voltage and frequency control using its excitation system and your speed governor control. So we'll discuss one by one. So let's talk about first grid connected mode. So in GCM or grid connected mode, you have power available at your end, but to manage your AC load, you can also take power from the grid. So grid is able to supply power, right? Now your PV, what do you think? Will PV operate at off MPPT or MPPT in grid connected mode? Yes, it will operate at MPPT. Whatever it's generating, it will try to, whatever is there, whatever amount of irradiation is there, it will try to generate the maximum available power and feed it back to the grid. And then you have your battery, which can either be charging or discharging, given how your PV system or your grid requirements are there. And your diesel generator, this will only help in voltage regulation. So let's say your voltage regulation is 4, and at your point of common coupling, the grid voltage is pretty different than what is available at the load side. So what you can do is you can change the excitation in such a way that your diesel generator could support voltage regulation, right? In isolated mode of operation, so we've all discussed these points clearly when we discussed on operation of AC microgrid. If you have any troubles, you can rewatch that lecture, but we'll once again do a short review of that whole concept as well. So your grid is no longer available, right? So if your grid is no longer available and you have a PV, what at what point will the PV be operating? Will it be operating at MPPT or off MPPT? So PV will operate at off MPPT. There's a reason because now you don't have grid available to you, right? If you don't have grid available to you, you don't know how the requirements would change, how much power will be. So the PV is very erratic, right? Uh, you could have Pmax at some level at one time, and it can fall to some level at the other time. So you would want to get stable power out of your PV. So you would want to operate it at off MPPT. Now your battery could your battery could either charge or discharge depending on how your conditions are there, and your diesel generator will take over frequency set. So we all know, right? The diesel generator is mostly so. The diesel generator consists of a turbine. Okay, so diesel generator consists of a turbine coupled with a synchronous machine, right? So the mode of operation is called isochronous mode of operation, where the priority of your diesel generator is to maintain frequency. That's why it's called isochronous mode. Okay, so how does a diesel do it? A diesel generator do it? It has a speed governor as well as an excitation system. So the speed governor controls the amount of mechanical power inlet to the rotor, and your excitation system controls the reactive power, which is input or taken out from your exciter system. So your diesel generator, by controlling its excitation, controls how much amount of reactive power could be taken in or taken given out from the system. So that's how your whole AC microgrid functions. So I won't go into the demonstration side of it because it's oh, no worries. I'm anyways going to record this lecture, so it doesn't matter even if you log off. So, but I'll ask you to be available. But even if you log off for some time, you just let me know if you want me to repeat something. Anyways, this lecture is being recorded and will be uploaded to YouTube. So I won't go into the demonstration part of it because it's much explained by the instructor, but and it's practically impossible because I don't have access to the demonstration part, right? So I don't know what kind of equipment, what kind of connections they did, or what kind of system they made, but whatever I could convey, I would convey from my side. So the grid connected mode, I'm just showing the case 3 and case 1 mode where you have all of your the batteries, PVs, and your load connected, and even your diesel generator connected. And in grid connected modes, the grid is connected to the microgrid is connected to the grid, and in isolated mode, it's working in an isolated mode, right? So both of these shows what I wanted to show was even in RTDS, if you model them as static, you are not modeling the dynamics of it. You are not modeling the control algorithm as such. You can see that the waveforms are purely sinusoidal, and the waveforms are pretty what you can say. They are free from harmonics. And in the isolated case, as you can see, we have some mm, it's very less, so I won't say it's in the scale is kilo ampere and it's 0.00002, so it's very less as per se, but the I grid is equal to 0, and all of your battery, your generator, and your PVs are matching how your load should be properly balanced. So that's the operation of AC microgrid. It's fairly very easy because you don't have much to do here because you just connect your system with your grid. That's how an AC system works, right? So let's talk about DC microgrid. So the operation and simulation and modeling of DC microgrid is something which is very difficult. One, because you have a lot of conversion stages. You have DC to DC, AC to DC, DC to DC. So you have multiple conversion stages. Even though you have a DC microgrid, still there are conversion stages, which causes what happens usually is that some amount of power could be lost in these uh, due to conversion efficiency, right? So but still it's much better than coupling DC to AC microgrids as per me. So in this, the instructor took a standalone DC microgrid system which had a DC bus coupled with PV panels which had a boost converter. This is a boost converter. Then you had diesel generator, which is converting from AC to DC. Then you had battery, supercapacitor, and you had wind as well, which was converted from AC to DC to DC to DC. And you had three loads. These all of these loads are basically DC. Some of them could be critical, some of them could be non-critical. So to control a DC microgrid, because you have to set the voltage reference. So in this voltage reference, you check how much amount of power you can take from grid, if at all you can take. So uh, so so if you are taking power from grid, let's say, then you devise an energy management scheme. So this is called an energy management scheme. So we talked about last class. So there's power management scheme which controls the power flow across the whole DC grid, and energy management scheme controls how much amount of energy you can derive from which sources and set the normal set points to be able to check, right? So let's start with, let's say you have enough grid resources available to meet your load, right? So if you have enough grid resources, you will check what is the situation of your battery. So if your battery is greater than 90, that means it has reached its highest point. So what you do, you set the PV and wind to bus regulation mode. That is, you set them from off. Oh, my voice is lower. Just a second. Yeah, so I feel this should be okay, right? Can you just tell me if it's okay? Yeah. So it was set on automatic. So, okay. So if your battery is greater than 90, so that means it can't take much stress, right? So whatever you're generating from your PV and wind, if they are working on MPPT, you won't be able to soak it all in. So what you do, you set them at bus regulation mode. What is bus regulation mode? That is generate only, which won't cause your bus to the high influx of power or change the voltage status of your bus, right? But let's say the SOC is not yet 90 degrees. So what you do, you set your PV and wind at MPPT only and let your battery charge. So this is one way. Let's say grid doesn't have enough power to meet your load. So what you do, you check whether or not you have come to your lowest point of your SOC. If you've not come to your lowest point of your SOC, you discharge your battery in such a way that your PV and wind are still working on MPPT, but your battery is discharging to fulfill the amount of to fulfill the deficit that is there. But let's say if the SOC is less than 40 degree, you would now rely on your DG because you don't have any other reliable source of power for your DC microgrid, not a DC microgrid, DC microgrid, to be able to maintain the bus voltage. So then you check if your DG could meet the deficit. If it can, you set your battery to charging and let the DG meet the deficit of the load. But let's say if it doesn't, so you move on to D point. So let's discuss in detail all of these points. So first, let's say that all of this made sense and you came to this C point. So what is exactly this C point? Oh, C is just starting. So what you do, you just keep on checking what is there left on your how what kind of energy management scheme you could. So you again check everything again. Let's say the DG is not available. So who would be responsible to supply the remaining amount of power, the deficit? So you check your battery SOC again. If it's less than 40, you discharge your battery in such a way that you meet one critical load, all your critical loads. It's not just one critical load, all your critical loads plus two non-critical loads as well. But if your SOC is less than 40, you check if the SOC is less than 30. That is, you have a leeway from going from 40% to 30%, and you check. If it's not less than 30, if it's between 30 and 40, you discharge your battery in such a way that you meet a critical load plus one non-critical load. But if your battery is less than 30 and you still want to supply, you don't have power to supply your critical load, you discharge your battery to meet your critical load. Now, let's say your DG is available, but it's not able to meet the deficit. Then again, you check your SOC. So if your SOC is less than 30, you discharge your battery. If it's not less than 30, you discharge your battery in such a way that you meet critical load plus two non-critical loads. But if it's less than 30, but between 20 and 30, you only discharge your uh, battery in one for critical load plus one non-critical load. Else, you only discharge your battery to critical loads. So it's important to set these energy management schemes. So what they do is they help you in maintaining your resources efficiently. So your battery, it should not be degraded to a very low level. It should not be such that you are doing everything you have available at your resources and the resource adequacy. So this whole thing is called resource adequacy. So what you're doing is you have adequate resources, and what you're doing, you're meeting every kind of load, which is not required. You don't have to meet your non-critical loads. Let's say if you have residential loads and school and hospital loads. So you would want to meet your school and hospital loads first, not your residential loads, because they are primary. They are not. They are secondary. Your primary customers are your critical loads. So these energy management schemes help in maintaining the resources, which is responsible for efficiently maintaining your resource. Okay, so moving on, if you have, let's say, two local DC grids, they can be coupled using a bidirectional DC to DC converter, which can help in maintaining those two remote grids and combining the whole efficiency, combining in such a way that it can enhance the efficiency of the grids. So let's talk about it. So, but one thing is very difficult to do it. Let's say if your one case 58 volts and the other was in 56 volts, so maintaining at the interconnection point, the voltage should be uh, uh, so at point of coupling, your voltage should be same. So that is something that you have to maintain in your interconnection stage. So let's talk about the benefits of interconnecting resources. So what do you feel would be the major benefit? Can you tell me? I mean, you have two different kinds of microgrids, all both DC microgrids, both are independent in nature. What can be one benefit that could help us by virtue of their interconnection? Can you think of something? Okay, so let's say that if you have a larger variety, yes. So if you have a larger variety of system, let's say you have a larger system, you would be able to cater a larger amount of loads. Let's say DCMG2, your loads suddenly become the power to be consumed by the load suddenly become higher than the generation available. Interconnection would maintain that you can trade power from, yes, at one place is more, yes, and you can trade power from each other. So one thing, you creation of a larger and more robust system. So you can efficiently meet your resources by having these larger systems available at your end. By this way, you can also enhance your reliability and resiliency. So you could have reliable power supply if in case your load demand goes higher than your generation available in your local area, and resilient, it can make you resilient. Let's say you had a sudden removal of generation at your end, so you could import power by having this interconnection tie line. It could improve efficiency, so by installing more renewables you can also efficiently manage these resources, your loads. What can be more? Mm, yeah, you can trade power, right? So power trading could be one thing, and so I leave it to you. There can be many benefits, right? So these are some things that could benefit. So and already these interconnecting two different DC microgrids could make sense, because remotely what you do, you usually have the DC microgrids at remote locations. So if you have two remote locations available at two different cities, let's say, and you have two independent microgrids over there, you can just interconnect them using a bidirectional converter so that both of them can support each other when in need. So that is something that you could do in DC microgrids efficiently, because you don't have to synchronize anything, just voltage needs to be synchronized. The voltage at tie interface should be same, but you don't have to do any frequency synchronization, anything else. So it's just your interconnection tie lines should be at same voltage level. So for this, they used a system architecture in which they had two DC microgrid, DCMG1 and DCMG2, which are connected using H-bridge converter. This is an H-bridge converter. It's a kind of isolated converter because it has a transformer in between. So whenever there's a transformer involved, these are isolated in converters. So it converts DC to DC, and it's an isolated DC to DC converters. So it could this transformer could help in stepping up or down your DC voltage in such a way that the tie at interface, both of these could be same. And this is how you control. So there are two regions. So let's say if so, this is region A and region B, right? No, region one and region two. So in region two, which is shaded blue, you support power from DC microgrid two to DC microgrid one, because your available um, what you say, your available voltage at this interface would be more than your available voltage at, so voltage at one end is greater than the voltage at the other end, right? So you would be able to better support because of supplying real power from higher voltage to lower voltage. And in region one, you support power from going into the opposite direction, from the microgrid one to microgrid two. So that's how you develop the system to be able to support your interconnection spaces. Okay, so this is one way in which you can do it. So this was about operation of DC microgrid. Fairly easy, right? So you have uh, independent DC buses. You can just connect your loads, connect your storages, and then you just devise an energy management scheme to help uh, so that your battery is managed effectively. And you can have interconnection because the interconnection of DC microgrids is fairly very, um, it can be done fairly easily. But what if you have a DC AC microgrid, which is a hybrid, or I should say AC DC microgrid, which is a hybrid microgrid, right? So, so what you have here is you have your AC bus connected to this one bus, which has 16 steps of OLTC, and OLTC is the online tap changer. So it's a voltage regulating device. So it's used when you want to regulate voltages, and it's connected between the utility grid and your distribution system, which is a 33 bus distribution system. So this is a 33 bus distribution system. I should say IEEE 33 bus. So in bus 5, you have connected your DC microgrid. So this is DCMG. And at bus 22, sorry, yeah. And at your bus 22, you have a separate microgrid, which is an AC microgrid, right? So, so what you want to do is you want to regulate voltages at bus 5 and bus 22 because they are connected to renewable resources, and since there are two different kinds of microgrids, both could be could influence how the voltage of your buses could be in real time. So what you do is you provide real time information, real time voltage information from all of these three buses to support the necessary voltage regulation at all of these buses, right? So for voltage regulation, what do you have? So you have an OLTC, which is an online tap changer, and you have a DStatCom, which is a distribution static compensator, right? So it's a power electronic device which is able to compensate your voltage regulation by taking in power when the voltage is greater than the certain amount, and losing power when the voltage is in when voltage sags. So there are two different. So you have two different kinds of what you say, voltage regulation device available at your end. So I would like to say one thing. So your OLTC, it's a slow acting device. So it's slow because it has mechanical switches which are configured to different taps. So it has 16 steps. So there are 16 taps. So whenever required, the mechanical switches work in such a way that it moves the switch up and down so that your tap could be increased or decreased given the need. And this helps in maintaining the 10% band, which is 1.9 to 1.1 pu of voltage. And at each step, since there are 16 steps, at each step, your voltage is controlled by 0.000625 per unit. Always remember this. So because of this, you are able to get at least 0.00625 change in voltage if you move your step up or down, given it's a regular position. So what you want to do is you want to have a coordinated voltage control over the whole system in such a way that voltage at 5 to 22 and 1, the voltages at these buses are regulated while compensating for the power which is being demanded or being input from those ends. Now, for this, the instructor student, Dr. Gururaj, which also joined our department, electrical engineering at IIT Kanpur. So he's a professor here. So so he has taken the excerpts from his paper. So he has proposed a coordinated voltage control scheme which works without communication. So you don't require communication at all. So there are three stages of grid operations. So before going into CVC, so so the main purpose of CVC or coordinated, do I have so coordinated? So this CVC scheme, what you want to do is you want to control your reactive power in such a way that magnitude of voltage at uh, the voltage regulating the buses at which you want to have voltage regulation is optimally compensated, right? So you employ this scheme to optimally utilize the available voltage regulation devices, right? So this voltage regulation devices, what they do is they tend to increase or decrease their reactive power compensation by either taking in, soaking in, or giving out, so that it can help in voltage fell or voltage sap. So there are two kinds of these techniques are of 2 points. One is coordinated, in which a central coordinator coordinates the control. So that means it requires communication. And the other is decentralized, right? I should say centralized, right? The right coordinated. So centralized, and you have a centralized central operator, and in decentralized, you don't need communication because all of them work on their own by using this CVC scheme. So let's come to the benefits of this scheme. So there are only two benefits. One, voltage regulation. So the main purpose is to regulate the voltage at buses that you want to manage, and third is optimal power flow. So you are also controlling how much power is flowing from which end, reactive power mainly, so that efficient power management could be there, right? Now, in this grid operating stages, there are three stages. One is a steady state, one is dynamic state, and the other is transient state. So in steady state, you have you have loads. Loads can switch, but the quantum is very small. So that means only small switching is there for small loads. And then your reactive power, although you have a very high reactive power available to you, but since the loads are the quantum of load switching is very small, the Q needed is less than 4%, 40%, sorry. And your voltage is in feasible band. Right. Now, let's say your VM is greater than 0.9. You have your voltage is in band, but your required Q is greater than 40%. That means you need more reactive power to be able to still maintain that voltage. What you do is you limit. So So basically, this is when large load switching is there. So the quantum of switching is large. So you what you do is, since your voltage is still in band, you don't have to supply more reactive power. Why? Because if you have reactive power available to you, you would utilize it to keep it as a reserve, so that once a difficult situation comes in, let's say when you need a very high amount of reactive power, you would want this reactive power then, right? So if you start using your reactive power right now to maintain the voltage at 1 per unit, which is not required because you are still in the band, so you won't do it, right? So what you do, you limit your Q from various is limited to 40%. So the rest of it could be used for reserves, right? And voltage is still in feasible region. Now, the dreadful thing would be if you are in a transient state when you have a very high amount of uh, load switching that is generally there due to faults, right? So let's say you got a fault happened, your V is not in 0.9 to 1.1. So what you do, you start pumping reactive power up to 100% of the rated capacity of your available voltage regulation devices. So these are the three operating stages of your grid, microgrid. Okay. So what the instructor the or Guru Raj proposed, he proposed a new CVC scheme. So CVC schemes existed way before, way long, but the problem was they didn't take into account three things. One, availability of devices wasn't taken into account. So if there was something, so you've heard, right? If something is if something is wrong, you tend to fix it, right? So you first need to know what was wrong. It like this. So why need CVC scheme? So first, availability of devices was not taken into account. So you could issue control commands for your devices, but what if the device is not available in the first place, right? And the second thing was that you didn't take into account your slow acting devices. So your OLTC, which is a slow acting device, it takes time to pump power back to the system, right? But your D STATCOM, being a switching device, being a power electronic device, it's very quick, right? The response time is very quick. So to be able to better judge how much quantum of power is needed, what you do is you would want your system to respond slowly so that you could check if your slow acting devices are also working or not. Because OLTC, even though it's a slow acting device, it's something that is better able to regulate the voltage at the bus at which it is connected, right? Because it's a transformer at the end of the day. So you take into account delay for slow acting devices. So, so these were some major issues that the new proposed scheme proposed, and uh, they the CVC scheme was able to propose this in a better way. So let's talk about how. So if you let's say have some other doubts, you can also stop me in between. Otherwise, what's the fun of these online lectures, right? So yes. So this is a new scheme that. So let's talk about this new scheme. So in this new scheme, there are three stages that he proposed. So the operating I'm just saying stages. I just talked about operating stages of the grid. So let's say operating steps. That would be a better operating steps of new CVC. So the first step was to identify the operating stage of the grid, right? So you have all the information available to you, but if you want to start proposing something, if you want to start proposing a control command, you would first want to know what is the stage of the grid, if it requires help or not. If what if you start pumping power when it doesn't require help, right? So you first find out, identify the grid stage, which is done in this block. So you check what is the status of your grid. So that is the first thing that you do. You move on to the second stage. You check for the availability of devices. So so you check if your OLTC is available, if your DStatCom is available. I mean, what all components do you have right now in your uh, stage? Then you issue master or slave uh, commands, right? So you issue master or slave commands. That is, you check what kind of role what a regulating device deserves. So let's talk in depth about. Do I need anything else? Yes. So let's talk about here. So let's say you check your operating conditions. So let's say you got that, okay, your voltage is not in the operating range. So that means you've propagated to a transient stage. So in transient stage, your fast acting device, since it's a fast acting device, it takes the role of your master, and your DC microgrid and your OLTC take up the role of slaves. What is master and slave? Your master issues the commands first, and then after their commands, the slave commands are issued. So slave works in a lower hierarchical order. So your master works first, and then your slave works. So that's how it's done. So similarly here, you see that in your transient state, you give the dstat or your grid side converter from your wind, the master role, and your DC microgrid and your OLTC is given the slave role. And out of that, you check how much of the reference is available, if it's isolated or if it's out of range. So then you move on to step C. So yeah, in step C, you measure the VM for all the OLTC, your DCMGC, and your DStat. Since they are now issuing commands, so you should be able to check if the voltage has been restored or not. If it's still not restored, you again check if the command issued of your reference queue for your DStat and your uh, wind side GSC is 100% or not, and then you continue checking till your voltage is back in the feasible range. Let's say that your voltage is in feasible range. What you do? So your OLTC and your DC microgrid, which are slow acting devices, they take on the role of master. So why they do that? Because you don't need the operations of DC. So first you check if you really need the help of something. So the slow acting devices come into place, and you check if you require help from them, if Q is there or not, because your voltage is still in the feasible range, right? Then you increase or decrease taps accordingly for the OLTC. For the DC microgrid, you issue delay period if there is a delay period required, if your VM is at the required stage or not, etc., etc. And for the DStat, you also issue delay period because the OLTC is a slow acting device, so you would want your fast acting devices to operate at a later stage. So that is something that you do. And the third issue, since I've already talked about it, it's the issuing of the time delay. Issuing time delay, right? So this time delay is, I'll just rebus at X position into OLTC tap divided by VOLTC, right? So this is how you issue your, just write it like this, your time delay pulses. So anything up until now this point, any issues, any questions? So I won't go into detail on how each and every component works. I mean, sir has covered beautifully. I'm just giving you a brief overview. Because if I start covering the demonstration, I won't have time for taking up doubts or anything else. So any questions? Okay, let's move on. So next, the instructor talked about parallel inverter operation. So we have, uh, so first of all, why do we require parallel inverter operation? So we have renewable energy available, right? And most of the renewable energy, PV, it's basically connected to a PV and wind. So because it's DC, so in the wind, what is it? It's AC DC, then DC AC, right? So it's connected to an inverter at the end of the stage. So most of the PV and wind plants consist of these identical parallel inverters. So we conduct in parallel because we want to increase the generation capacity from all of our resources, right? So one parallel operation helps in increasing generation capacity. So so this is not something that is new. We have parallel operation of synchronous generators as well, parallel operation of DC generator as well. So parallel operation is something that we are doing since the beginning for all the generations. And this is something that is applied to the DC as well as wind plants as well. So all the inverters, they are connected parallelly, are basically current controlled inverters, right? So they act as current sources. So so yeah, so this is something that is being done since the very end. So this is a something of interest. So what we have is, so you have an inverter, and then you connect it with an LCL filter. So this LCL filter acts as a, it gives the passage only to the lower frequency, so that higher frequencies are stopped before entering the point of common coupling. So you have LCL filter connected across all of these parallel inverters, right? Now, when you have inverters connected in parallel, there are two main, okay, there are two main currents that flow in the system. So one is an interactive current which flows within the inverters, and the other is the common current which is fed to the grid. So both of these uh, have their own merits and demerits. So at the end of the day, you would want all of your current to be made available to the grid only, so that none of that is bypassed to flow between the inverters only. So that is something that you want. And usually these interactive currents, these have high frequency oscillations, because why? Because if they're not high frequency, they won't be, since they are not being fed to the grid, these high frequencies flow between the converters only. So these go from this place to this place to this place. So in between inverters, these inverter currents flow. We'll check everything. We'll talk about everything, but this will start from what is the reason for. Yeah. Why they are producing in parallel operation. Yeah, I'll tell you. I'll tell you everything. We'll talk about in detail. So what's usually happening is you have high frequency components of currents available as well, right? So this LCL filter is not able to filter out these. So it's not able to filter out these. No, sorry, it's able to stop these currents to flow to the grid. But what they do is it's not able to control them to flow between the inverters. Now, how do they flow from inverter to inverter? It's something which is very it needs to be derived. So let's start. So I'll give you a brief, I'll give you a disclaimer. So I won't be deriving anything from scratch. So if you want me to derive something, it should come from you. I'll just give you how to derive these things. So I also had to look to the papers or references that that sir provided, and I started deriving as well, but they were quite lengthy. So, and sometimes, so I won't be able to give you right answer here, then here, I mean, directly here, right? Well, I will also derive with you, but the derivation won't be perfectly clear. So if you have problem, I'll still derive, but not online. I'll derive it offline and then upload with the lectures. Because I've already derived half of it, why not complete it? So, so what you have is, so you have your reference current. So since it's a current source inverter, it's controlled through a controlled through current. So what you do is you feed in a reference current and you check what kind of current it is feeding back to the grid. So this current is being fed from here to here. So it's a feedback loop, right? And this error signal is then fed into the it's fed in such a way that this control algorithm produces a open uh, circuit voltage at the inverter end. And at the inverter end, it's connected to an LCL filter, which is then connected to the point of common coupling, which is feeding power to the grid. So this is a single inverter control system, right? Now, for a single inverter, if I need to write the transfer function for it, it would be I21 G1 times I reference, right? Because your input is I reference 1 and your output is your current, which is being fed to the point of common coupling. So this is your transfer function, and your transfer function, which could be very easily found out. It would be VO1 by E and I21 by VO1, right? So you have source here and you have your error function here. The first thing you would be VO1 by by E, which is it would be directly uh, controlled through this. So it's the output is the E gives VO1, and then your I21 is directly connected across VO1. So it's you can easily find out there. So this is your G1, right? So you can easily see that your output current. Okay, so your output current is directly a function, let's say, of your error, which is your reference current, right? So you can easily see that it's just simply the function of your reference current. Now let's connect everything let's connect one more inverter in parallel, and let's leave this side for now. Don't include this side because for this you would require gain of this current controlled active damping algorithm as well, right? So if you don't have it, just forget it for now. Now, if you would want to write the transfer function for this, it would be in the form of matrix, right? You can easily write it in form of matrix. Why? Why can you do that? So I'll tell you one. Just let me write one equation. So as you know, you have two different sources connected here, right? You have VO1 and VO2. So to be able to find out the accuracy of both, what you can do is you can use the concept of superposition. You can just connect one VO1 at one time and then short the other time the other one, and in the other you can just short the first one and then see how VO2 reacts to the grid. Now, if you see at this point of common coupling, won't the current flow from this end to this end? It could, right? There could be a flow of current from this end to this end. And in the other side, this flow of current would be in this side. Now you would be thinking, let's say that VO1 and VO2 are equal, all the parameters are equal, your currents would be same. So if your currents are same, they would cancel out. But that's not true because you have inaccuracies in your system. So if you have inaccuracies in your system, your current would be you won't have same currents for the both of them. There would be one component that would flow from one convert inverter side to the other inverter, even after the algebraic sum being positive or negative, right? So so you can easily see that the current output from one side, that is I21, it is dependent on both VO1 and VO2. So if it's dependent on both VO1 and VO2, how would you be able to control your interference, or sorry, your interactive current to be able to give all of the amount of power that is being generated to the as a common current to the grid? So that is something that you need to do. So uh, let's talk about how you can do that. So I am again giving you a disclaimer. I will try to solve it and give you all everything with the notes, but I won't do it right now. So I will just give whatever there was in the PPT. Let me open it once. Hmm. So in his derivation, he derived G11 and G22 will be same, which were n minus 1 upon n Gp plus 1 upon n Gc. And you had G12, which is G21, your diagonals, which was minus 1 upon n Gp plus 1 upon n Gc, where Gp was plant transfer function without Lg, and Gc was the plant transfer function with Lg, right? And your Gp came out to be 1 upon S L11, L21, C11, 1 upon S square plus omega R square, and your Gc was 1 upon S L11 plus Lg C11 plus omega R square, right? And omega R and omega R1 were um, your resonant frequencies for both the conditions, right? Now, if these are your plant transfer functions, so what you require is how would your current look like? So your interactive current component was nothing but 1 upon n Gp d upon 1 plus Gpd, where d is your error signal to inverter output voltage transfer function, which is you can just straight away take it as d. You don't have to derive it. And it was IREF1 minus IREF2. And your common current came out to be GCD 1 plus GCD IREF 1 plus IREF. So you can easily see that your interactive current contains uh, uh, your difference of your reference current for inverter 1 and your reference current for inverter 2, and your common current was basically the addition of both. Now, since you would want this interactive current to be stable, you don't want it to be an interference for your system. What you do is you could just set IRF1 equal to IRF2, and your I interactive current will vanish right straight away. And if it's not possible, let's say if it's not possible for you to do that, what you can do is you can check if the poles of the characteristic equation of both of them lie in the right half plane or not. So in S plane, which is drawn something like this, I hope you all know what an S plane is. So this is your S plane. So you check your characteristic equation. So your characteristic equation for interactive current 1 plus GPD, and your characteristic just for common current 1 plus GCD. Now you check the poles. So what are poles? So you equate all of them to zero and you check what is the value of S. So the point at which the transfer function becomes infinite is called a pole, and the point at which that's what is called pole. And you check where the poles lie. If your poles lie here in the left half of the plane, then your system is unstable. If your poles lie on the right hand side of your plane, then your system is stable. But what if the pole lies on the boundary, right here? So no, left is unstable, right hand side is stable. Just a second, I'm confused. Hmm. Lecture. Yeah. So yeah, second. Yes, I'm wrong. Yeah. So yes, it should be the opposite. So your right hand side is the unstable region and your left hand side is the stable region. But if it's in the boundary, your system is marginally stable. Yeah, yeah, it's marginally stable. Yes. So that is something that you can check to see if your inverter current, if it all, sorry, interactive current, if it all is there, could make your system go unstable. If the characteristic equation has poles which lie on the left hand side, you have a stable system. But if they don't, you have an unstable system. So just a second. Hmm, my bad. I just wrote. Okay. So the pole should not be on the right hand side. It should be on the left hand side. I stand corrected. So that's it for the parallel operation. So if at all the interactive current is there, which is basically the subtraction of your reference current from your first inverter to the reference current of your second inverter. If at all it's positive, you can check if it could make your system go unstable by checking the poles of the characteristic equation. So that is something that you do to check if the parallel operation of the inverters is possible or not. So that was it for parallel operation. So let's move on to the next topic. Oh, I have six charts. Yeah. So yeah, thanks for correcting. Otherwise, I would have written right hand side. No. Okay. So the next topic that instructor covered was the effects of harmonics and what are the mitigation techniques, right? So what are harmonics? So you have a sinusoidal AC wave, right? So it oscillates at 50 hertz frequency and it goes from VM to minus VM. And that's your perfectly fine looking, stable looking uh, AC wave. But what if you get something out of from your, let's say, some component and you check the uh, output of that AC wave? What if it doesn't match perfectly to that AC wave, right? So, but it's taking input from the AC grid only. So it should be producing AC wave, which is 50 hertz frequency with the same looking graph. But if it's not like that, what exactly is happening is that that waveform is plagued with harmonics. So what are harmonics? Harmonics are basically your your unwanted frequencies or your unwanted frequencies available in your available in your AC system, which make your AC feel distorted from your regular or how it should look uh, as before. So let's say you have this fundamental first harmonic. What is fundamental first harmonic? Is your 50 hertz frequency. So your fundamental first harmonic looks something like this, right? It has a peak, it has a crest, and it's oscillating at 50 hertz frequency. Your second harmonic, which is two times your fundamental frequency, which is 100 hertz, so it rotates twice the speed of your 50 hertz frequency, right? So it's not perfectly matching your AC sinusoidal wave. Similarly, you could have third harmonics, fourth harmonics. So what they do is they distort your waveform. So you were supposed to have this purple waveform, but it's plagued with this green waveform. What you get is this right waveform, which is not looking something which is there in the which is how it was supposed to look. Similarly, your third waveform and third harmonic and fourth harmonic, they distort it in such a way that it's plagued with high frequency components. Now, these high frequency components basically what they do is they cause the power quality of your waveform to be very bad. So they have certain effects on your system. So let's talk about that. So these harmonics are also configured in the form of their sequences. So the the fundamental harmonic is your positive sequence harmonic. The second harmonic is your negative sequence, and their third harmonic is your zero sequence, also called as triplen harmonic. They triple the normal harmonic, and this cycle continues, right? After every three uh, frequencies. So, so what they do is usually, since the positive sequence has forward rotation, it causes excessive heating in your conductor. So the main harmonic effect of your positive sequence harmonics is that they cause excessive heating effect on your conductors. Similarly, the negative sequence harmonics, these are reverse harmonics which rotate in a reverse phase. So they cause issues in your motor torque. And one issue they have is their motor torque, and this is usually because they are rotating. They are out of phase of the normal fundamental frequency, right? So if they are rotating out of phase, the motor torque, which is being generated using a rotating magnetic field, it would be plagued with these harmonics, which would cause torque problems. And zero, they don't do anything. It's just that they add to the neutral to ground wires, which causes heating in that neutral wire. So so the harmonics present in your system are a very what do you say, are a very um, serious power quality issues, because the as per IEEE standard, the total harmonic distortion of your AC waveform should be less than equal to 5%. That means that the AC waveform should not have frequency components which are a value higher, which are a value higher than 5% of the how it should behave with the normal frequency. So this THD is usually calculated using Fourier analysis. So I'm sure you must have done this in your MATLAB simulations, where you do it through Power GUI toolbox, where you do the Fourier analysis and then you calculate the THD. So by Fourier analysis, what you do is you break, yes, you break the time series data to frequencies, and you check how much frequency component is available in the whole. Just a second, behaving, right? I don't know. Yeah. So so this is something that you do. So yeah, so it was a yes. So Fourier analysis tells what is the magnitude of the frequency component present at uh, present in your system. So basically, and then it checks the THD of the system. So um, THD is let's say you're checking of, it could be of voltage or current. Um, so you can have x1 square, x2 square, xn square divided by x1 to the whole um, square root over the bar. So this is how you can check the THD of your signal. So the harmonic distortion, which is usually present in your system, should not be there, and I mean it should be less than 5%. So that is something that you need to check when you propose a novel converter design or something which you want to propose, right? So that is something that should not be available. Hmm. Okay, so let's move on. So you can have multiple for these. You have multiple mitigation techniques available at your discretion. So you can have passive filters which are available in shunt and series condition when they can have hybrid conditions as well. And the passive filters are the most basic forms of your filters available to you. Let me write someplace. Let me hear it. I'll match the colors. So this is least expensive. So they are very least expensive and they also don't require much maintenance and they are easily built. But they also have some cons. I should pros, right? It's better if I write them with green pen. Hmm. And then you can have, and then your cons. We should also discuss cons since we are at it. What are the cons? I mean, what can you think of them? It's one, since the fundamental frequency that you need to pass from your system, uh, the the way that they should give is low impedance to the path of that size, right? But for that, what you need is you need a very bulkier system. The presence of inductors, capacitors makes your system feel very bulky. So your system becomes bulkier in nature. Second, so let's say that you tune them to adapt to certain power harmonics, right? Let's say conditions changed and your harmonics changed. And now you would need to change their tuning again and again. So they can't adapt. So they have fixed uh, filter tuning capacity characteristics, I should say. So these are the cons of your passive filters. Then comes your shunt or active filters. So the pros, let's talk about their pros. So one thing that they are able to, so one thing they're better able to do is they are able to adapt to your changing requirements. So they have a dynamic filtering. Second, they can eliminate a wide range of harmonics because they are dynamic in nature. And what else? Okay, so yeah, since they are shunt type, they are better suited for current quality issues. But they have their cons as well. One of the cons is that they have a high initial cost. And they have a complex design. So since this is a power electronic equipment, you need to design them efficiently. Then you have series active filters. So the main focus of series active filter is that they also have dynamic or adaptive filtering, suitable for voltage quality applications. Again, cons, high initial costs, and complex design. So I won't write for UPQC. You would have sensed that since it's a both series and shunt kind of active filters, what it does is it is suitable for both current quality and voltage quality problems, and it has dynamic filtering as well. But then again, the cost is high and the design is complex. So this is in a way what you can do. You can have these filtering your devices connected to your system to be able to mitigate power quality issues at hand. That can be your current quality issues or your voltage quality issues. So, so, so in the next slide, sir showed how he showed how a series active power filter in connection with the shunt active power filter was used to compensate the current quality and voltage quality problems. So he had again a DC micro. He had an AC DC microgrid where no, not an AC DC microgrid. It was a DC microgrid, and he had a PV array connected with battery and wind and some DC load. So with nonlinear load as well, because who causes these? This is something I don't not discussed, right? So I discussed everything related to harmonics. So what causes harmonics? Harmonics are caused by the application of nonlinear load. So can anyone tell me the example of nonlinear load and why exactly are they called nonlinear? So my question to you was, what are nonlinear loads and why are they called nonlinear? So yes, so nonlinear loads are basically your P devices. So these can be diodes, switches, etc., etc. So their VI characteristics. So you should, yeah, voltage and current. So VI characteristics are nonlinear. So when you have just a resistor, right? So when you have a resistor, so sorry. So when you had a resistor, yeah. So when you had a resistor, your current was directly proportional to your voltage. However, your current varied, your voltage varied linearly to it. But when diodes came, so your diode had something like this, right? And you could draw the other side as well. Hmm. So when your diodes came, they had this. So this kind of a graph is non-linear in nature because at one point the current is not varying proportionally to it, but with some voltage increase, the current is increasing exponentially. So these VI characteristics being non-linear in nature produces difference in how voltage and current should interact with each other and produces power quality problems. And these power quality problems are need to be sorted so that your uh, your system could behave as you want in the first place. Yeah. So he used a shunt active power filter and a series active power filter to figure out the power quality problems caused by this nonlinear load in connection to a DC microgrid. And as you can see, without compensation, you could see that the current waveform, the I yes. So the current waveform and the voltage waveform was very distorted. That is, they were plagued with harmonics, but after compensation, the harmonics were still there, but not as much. I mean, you can see, right? Okay, so yeah, so that was that's all that Sir discussed in this week. So let me give you a quick overview before we move on to questions. So Shibna, I hope that you're paying attention to. So we started with demonstration of operation of an AC microgrid because now we have moved on to that place where now we start demonstrating how all of what we have learned works in real life, right? So we talked about what grid connected mode is, how isolated mode should behave, and then we talked about some cases because demonstrating everything is not in my control. And then I talked about what a standalone DC microgrid behaves, the energy micromanagement scheme associated with it, how interconnection of two local grids would be, local DC grids would be beneficial for the system and for each other as well. Then we discussed how interconnection of two local grids could be done in real life, which is through an H bridge, which is an isolated DC to DC converter. Then we moved on to a simulation of AC/DC hybrid microgrid, where I showed how a coordinated voltage control schemes could be employed to bet to be bet to which is better suited to manage the voltage regulation in the buses at which the AC microgrid and the DC microgrids are connected. And in this coordinated voltage scheme consists of two types. One is centralized, the other is decentralized. The one proposed by the instructor is decentralized because it does not require communication. And the centralized, if you even employ it, will employ a communication where a central operator will take charge. So we talked about three operations of grid stages. One is steady state, in which there is load switching, but the load switching is very small. The quantum is very small, and the reactive power needed to meet that switching or to meet something is very less, which is 40%, and the voltage is in feasible range. In dynamic state, there is large load switching, but the voltage is still in feasible region. So what you do, you limit your Q to 40% so that you could have reactive power as reserve, so that if at all transient stage comes into play, you can use that reactive power as a reserve to empower your voltage. In transient state, what happens is your voltage is no longer in the feasible region, and you require Q from your voltage regulating devices to be able to maintain the V between the band. So we talked about how why the instructor proposed a new CVC scheme as opposed to the earlier present scheme available for the whole for the management of the AC/DC microgrid. It's because the earlier schemes didn't consider the availability of devices. That is, they didn't consider which device was available to give power at what time. And the second, they didn't take into account the delay that exists between the slow acting devices and the fast acting devices. The OLTC is a slow acting device because it is a mechanical switch which switches between different tap positions. And the power electronic devices such as these STATCOM are basically fast acting devices because they don't need a large amount of time to they don't need some amount of time to even start working. One thing that I want to tell is that OLTC here has 16 steps. That means at each step you can control 0.000625 per unit of voltage. And yeah, so the new scheme took into account the availability as well as the delay for slow acting devices. Then he proposed his new CVC where he identified three steps. One was identification of the operating stage of the operating stage of the system, where he checked what is the voltage, if it is in between the feasible range or not. And then after that, he checked for the availability of devices. And in between the devices that were available, he issued master of slave command. A master of slave command is a hierarchical control commands where the master works first and then issues command for the slave commands. And third, he issued time delay so that slow acting devices could also provide power and could start injecting reactive power simultaneously with fast devices. This is needed because let's say your fast active devices start providing power, and after some time your slow active device also starts providing power. You would pass the certain threshold, and your Q supplied would be very large to the Q needed. So this is something that needs to be controlled. It is through a time delay, which is issued using this logic. After that, we discussed parallel inverter operation, where we discussed why parallel operation is needed is because we want to increase the generation capacity from all the available PVs or wind plants, and we can just interconnect them by connecting them all in parallel, and all connected inverters behave in a current controlled manner. So we talked about the challenges in parallel operation of inverters. It's that the high frequency oscillation present in the interactive current component is there, which travels from one inverter into the other, and only the common current is passed on to the normal grid. So we talked about how this. Yeah, you can you can say online tap changer, you can say on, it's not online, it's online or on load. You can just say both, because both of them mean same thing, right? You are just changing them when they when the load is being powered. So it's given on load or online. One more term is there. Just let me. One more term is there. Mm, on circuit. It is also called on circuit tap changer. So it has three different. What you say? But basically, it's a tap changer only. So you can just. So it's connect when the load is connected, the taps are changed. So that's what my point was. It's not online, like surfing web. It's yeah. And then you could have yeah. So we was yeah. So how this interactive current comes into play is we talked about how the transfer gain of the whole system looks like, and how this inverter I interactive component comes. So one way is you can set the whole reference current same, but that is not something you can do because the parameters are different. Your requirements could be different. So what you can do is you can check if the characteristic equation, the poles of the characteristic equation should characteristic equations should not lie in the right half side of the plane. They should lie in the left right side of the plane, which is the stable region. And then you if they lie in the stable region, you can use the parallel operation, or if they lie in the unstable, you have to modify the gain of your system. Then we talked about effects of harmonics. What are harmonics? How they affect the system? They are usually the byproduct of using nonlinear loads, and they are usually the byproduct of their nonlinear loads, and they are of three types. One is the positive sequence harmonics, which are 1, 4, 7. They are in addition of three numbers, and then you have reverse sequence current, negative sequence harmonics, which are second, 5, and 8, and you have triplet harmonics, which are zero sequence, and all of them have different harmonic effects. The positive has an excessive heating effect, the negative causes motor torque problems, and the third one, the, the zero harmonics, causes the addition of voltage or current in the neutral to ground phase. Hmm. So what we want is, for a healthy system, the THD should be less than equal to 5%. THD you can find out using Fourier analysis, where you convert uh, your time dependent equations to frequency dependent equations, and then you can check what is the magnitude of what frequency. So we talked about what are nonlinear loads, and we talked about some of the mitigation equipments available at our discretion, and what are the pros and cons of each stage. So let's start with questions. So the first question is, dash transformation converts ABC to DQ0. So ABC, there are two kinds of versions. One is ABC to DQ and the ABC to alpha beta. So who can tell me the answer for this, and who can tell me what are the names for alpha beta as well, ABC to alpha beta? So what we want, why do we do is because sometimes managing three different um, uh, phase currents could become difficult to employ in the control strategy. So we convert them to DQ reference frame, which is direct axis and quadrature axis, or alpha beta axis, so that to have a better control scheme which only utilizes two different components. So who can tell me what is name what? So I remembered I talked about it in some of my previous lectures. So if you have forgotten, the ABC to DQ is called path transformation, and alpha beta is called Clark transformation. In some places, you can have Clark and Parkes transformation as well, both in connection to each other. I remember it's used in space vector pulse width modulation control of matrix converters. So matrix converters are your AC to AC converters. So in that, to be able to have SVP control, you need both Clark's and Parkes transformation. So the correct answer is A. Second, who can tell me the correct answer? Identify the correct statements. Yeah, this is fairly easy, right? I discussed it today as well. Maybe B. Not maybe B, it's actually B. So when your system is overexcited, so it has excess of yeah, yeah. So when it is overexcited, it has excess of reactive power available at its discretion, which it supplies to the system. So it injects reactive power when it's overexcited. Third, identify the correct statement. Again, so this should be very easy, right? So in an isolated DC microgrid, how would you connect your battery and supercapacitors? You would connect it using a bidirectional converter, right? B. Okay, so you're saying only the battery needs bidirectional converter, not the supercapacitor. Why? If supercapacitor, which has a higher power density, if it supplies power, won't it need to recharge so that it restores back to its normal power density? It would also require power, right? To come back to its normal density. So capacitor also takes power, right? It discharges as well as charges. So what should it be? So your battery would require a bidirectional. Yeah. So your battery requires bidirectional power. Supercapacitor, let's say if it discharges to the grid, won't it need to charge back? So if it would need to charge back, won't it be connected to your to a buck boost converter so that you can control it on your own? Otherwise, if you just plainly connect it to your grid, what would happen? It would charge whenever whenever it is required, right? So to create control over the whole system, you generally have it connected using a buck boost converter, which is a bidirectional converter. So the answer is C. Any questions, Ari? Got it. Yes. Just a second. Let me see if there are. Yes. Here you can see, right? So the supercapacitor also has interchange of power between the both. Yeah. And it's two bidirectional converter. Next question. So which one is the voltage regulating device? Fairly easy, right? See, yes. So both OLTC and your D STATCOM are your voltage regulating devices. So both of them can regulate the voltages at the bus at which they are connected. Now, an OLTC is connected between nodes 1 and 2, regulating the voltage at node 2 with respect to node 1. The voltage at node 1 is 1 per unit, and the tap position of OLTC is minus 10. Compute the voltage at node 2. Who will tell me the correct answer? So at each step, it can control 0.00625 per unit voltage. And now the question says that you have a voltage regulating node at 2 with respect to 1, and the voltage at node 1 is 1. So that means, and the position of OLTC is minus 10, compute the voltage at node 2. So minus 10 times 0.000625, which is 0.00625, right? So if you do the voltage, so what is voltage regulation? So VR is given, sorry, yeah, voltage at 2 is 1, no, sorry, your voltage regulation is minus 0.00625, right? So V1 minus V2 is minus 0.00625. So your V1, which is 1, hmm, just a second, no load minus load. It would be V2 minus V1. So V2, V1 minus 0.00625. The answer would be 0.9375. So your voltage would be less, right? Because it's connected to 1. So it is mod of V1 minus V2. Okay. So can't I have it written as V2 minus V1? Okay. But you tell me, if your V1 is at 1 and you have connected a OLTC which is minus 10, so your voltage at V2, would it be greater than V1 or less than V1? So it's decreasing, right? Yes. So the answer is 0.9375. Next question. So in the steady state operation of the transmission grid, the voltage magnitudes are regulated in the range of dash per unit. Very easy, right? We discussed at length today. Yeah, it's 0.9 to 1.1. Next, multi-parallel inverter system connected to the grid act as, yes, current sources. So all of them are act as current sources. So next, select the correct statement in the context of multi-parallel inverters. Hmm. This is also very easy, right? Okay, yes. Let's talk of all of them. So interactive currents don't flow into the grids, common currents do. And the problem of interactive and common resonance occurs in L-filtered inverters due to their first order nature. So this is untrue. So when you have only L-filtered nature, L-filtered inverters, so that's first order. So in first order, you don't have the what to say, you don't have the what to call them. Um, so you don't have a connection in which you can bypass this filter to be able to go to the next inverter, because the only, so this GP, yes, so this GP and GC, they will be first order in nature. If they are first ordered, their poles, what would happen to their poles if they are first order? Can you tell me? So if I have a first ordered filter, what would happen to the poles of the system? What is a first ordered system? Can anyone tell me? Only one pole, right? So if they have only one pole, so here, yeah, your GP and GC, they have, uh, first of all, they have this S, which we won't consider because S will be directly 0. You have this, right? So there will be two poles. Your the when you have a first ordered filter, if you will do the mathematics, if you just have L connected over here, the system will always be stable. It's a fact, because of first order nature, the system will always be stable if you derive the whole circuit. And if that system is always stable, you won't require, or you won't have the problem of invert this interactive current component and common current component, because you won't they won't cause instability in your system. So the third is also incorrect. So the first switches that are unstable if poles of their characteristic equation lie in the right of plane is, yeah. Next, select the correct statement. Yes. So nonlinear loads induce harmonic in the system. This is true. Harmonics can cause interference with the telecommunication line. Yes, yes. So the harmonics can cause interference with the transmission lines, because these are high power frequency components, right? And you've heard that high power frequency components could interfere with the radio, could cause EMI or radio interference. And DVR, which is distribution voltage regulation device, it's a you can call it a normal filter, passive filter, or anything. It is also a power quality mitigation technique. So all are correct. So distribution voltage regulation is a power quality mitigation device, right? Called distribution voltage regulation, right? Dynamic voltage restorer. I'm sorry, distribution voltage regulation device. It's dynamic voltage restorer. Since it's a dynamic voltage restorer, yes, yes. So since it's a dynamic voltage restorer, you are trying to check if your voltage sags as well. So it's 10th, for an inverter with an LCL filter to be stable, it is required to ensure the stability of. So you just need the stability of what current? B, interactive current. Correct. So you just need to check if your interactive currents poles lie in the left half plane or not. That is it. So I've discussed all of the questions I wanted to discuss today. I have discussed all of the things. If you have doubts, I can take doubts. I mean, I know just as much, but still you can ask doubts if you have. So you regularly get these weekly feedback forms, right? For what they say is this, for problem solving sessions. Do give them. I mean, um, objectively, so that I can check, and then if there is any need required, I can modulate my lectures in certain way so that you which is able to fulfill need of everyone. I try to do the best I can. Some of these things I'm also not familiar with, because my area of expertise is completely different, and it will listen record section of sir due to internet issues I didn't concentrate. Yeah, yeah, yeah. Please do that. So, so some of this is also very new to me. I go through it. I go through references, but given that I work in a completely different area, it's I mean all of these smart grid. So can you please upload faster? See, that is my whenever I receive the recording, I straight away upload. I don't take time. Usually the PM at IITK, they take time to send me this record. Since Saturday, Sunday is the holiday, so they usually give it to me on Monday or Tuesday. So that's that's the problem. But yeah, as soon as I get, I generally upload. Yeah, I only was late last week and last week I had gone for some stuff at New Delhi, and last week I was at home. So, any other questions? Shibna. So please, Shibna, go through this. But your explanation is, even though your domain is different, of course, this is the continue of parallel inverter session. So one session continue. Oh yes, the whole session. Yeah, I'll derive it. I don't know if I would. So I derived it. It's coming out to be a bit different. So I don't have access to the whole derivation, right? So I'm trying to derive it on my own. But as much as I do, I just upload it with this reference lecture. That's for sure. Any other explanation? I mean, I try to give my best. I sometimes can get corrected as well. Can you add electrostatic shield, which you see? See, ID. See, I don't work with data sheets, Dharani. I don't even know what IDTs is. What is ITDs? Is IDT a company? Let me search. I, inverter duty transformer. That is reason for interactive. Oh, hmm. Just let me see. Okay, let me see. Yeah. I don't think so. This interactive transformer is same as the interactive current. Dharani. Yeah, electrostatic shield we use to shield our stuff from electric fields, right? The difference between electric fields. But the inverter duty transformer, I don't think that's for. Oh, I doubt interactive inverter duty transformer. Inverter inverter duty transformer is not something that is for interactive current, right? I don't see anything like that. I read like harmonic or yeah, I mean electrostatic. So when you have different this difference in electric field, so that causes static electricity and which causes voltage pulsations. So anything related to power quality could be associated with the harmonics, and it is used to protect that from the harmonics in the voltage. But I don't know why you wrote interactive duty inverter duty transformer. That is the reason for interactive. I mean, okay, so okay, so I'll also check. You also check. You all, anyways, know you can contact me on LinkedIn, right? So just if you find anything, find any material related to it, do tell me. I'll check it with you. Yeah, but I'll try to include that whatever I've derived, I'll try to include so that it can serve as a basis for you to derive it on your own as well. If I'm not able to do it, I mean, um you are much more, what you can say, you are more familiar with these derivations than I am, because I did my BTech in 2021. 3 years since I've lost touch with the whole, the GATE syllabus. So, but as much as I could, I would definitely add so that you can just build on that. Okay, so I'll close this session. So if there are no more questions, thank you for both of you joining. It was nice that someone was there to listen. Yeah, welcome, Dharini. Real project, mainly best project. Yeah. If you find this, so do think of joining what you say, masters or a PhD graduate program, right? You would be able to use, if you want to really deepen your knowledge in these areas. This would really help. But anyways, industry I feel is much more advanced than what you do here in academics. So you, in industry, you gain practical knowledge, right? Here you don't have practical knowledge. What you have is books and research papers that you read to get it. But yeah, if you feel that you can, if you are really able to do well using these projects, so do consider a graduate program, an MS, an MTech, or a PhD program. Yeah. So thank you all for joining. If there are no feedback, nothing. Yes, sir. But if we relate that knowledge in project, yes, yes. But for that you need industry, right? Someone to give you practical equipments to. I like I don't have that much. I mean, if you see my area, na, what I work in, you would be like, how are you even teaching me the subject? Knowledge to us. I'm not giving you anything. Okay, so I'll stop this lecture. Thank you for joining, Dharini. Thank you, Shibna. Okay, bye.